Alright, so this is our first video in Unit 3. And this video is going to go over the three different forms of a quadratic function. So our last unit, we went over absolute value functions. Now for basically the next 2 or 3 units, we're going to switch and focus on quadratic functions. Alright, so the first form is called Vertex Form. Now, in Vertex Form, you may want to pause it so you can copy this stuff down. In Vertex Form, this looks exactly like our basic transformation form. If you look at it, it looks exactly like the absolute value function we've been using, where it's a x minus h squared plus k. The only difference is that we have right here, we have this squared instead of the absolute value bars. Those are just parentheses now. So essentially we have the same type of function. It's just going to be squared instead of absolute value bars. What we can learn from this equation is the transformation rules are the same they've always been. So A is vertical stretch or compression, H moves me left or right, K moves me up or down. None of that changes. My axis of symmetry, which is going to be on a couple different slides, so I'm just going to draw a picture real quick. The parent or just regular quadratic function looks like this. The axis of symmetry is an imaginary, well, if I draw it right, is an imaginary dotted line that just goes straight down the middle of the quadratic and cuts it in half. So if I folded hot dog style, as we used to say in elementary school, we would see that the graph would fall on top of each other. Alright, so that's my axis of symmetry. And then the vertex is just like absolute value. The vertex is either going to be the highest or lowest point on the graph. Intercept or factored form, I'll really use both kind of interchangeably. Intercept and factored form looks like what you see below. So here. So intercept or factored form lets me know what the x-intercepts are. The name is not creative. We call it intercept form because it tells me what the x-intercepts are. Those intercepts occur at R1 and R2, which I know this is an extremely generic mathy equation right now, but we'll get down to some examples in a second. The axis of symmetry we can also find from this. It's just not as straightforward. So the vertex, the axis of symmetry, happens at x equals h. It's just the x value of the vertex. But here, if I have, let's say this is R2, this is R1, my axis of symmetry is perfectly in the middle of both x-intercepts. So the axis of symmetry would be at the x value between R1 and R2. Again, this is the notes slide. We have examples in a minute, so just make sure this is written down so we can use it in class. All right, last one is standard form. Standard form essentially tells us nothing. We're going to spend most of our time converting out of standard form. So if I ever give you standard form, most of the time we're either going to factor it or do something called completing the square to turn it into vertex form. Because standard form tells us nothing. To find the axis of symmetry, it's this crazy equation. There's not a great mathematical explanation for why this works, or not a simple one at least. So just copy down that the axis of symmetry is going to be at negative b over 2a, and that's at the x value of the vertex. And then we'll do some stuff with that in class, but just have that in your notes. And the only thing that we can really get from this is the y-intercept is just c. But you don't have to memorize that stuff. Just have it written down for the future. All right. So here I'm going to graph 2x plus 3 squared minus 2. So to do this, when we're graphing a quadratic, you want at least 3 points, the vertex being one of them. So here, I should have asked the vertex here. I'll do it over here. So the vertex, my vertex is HK, just like absolute value. Just like absolute value, H is a liar. So I have x plus 3 inside my parentheses, so my vertex is going to be negative 3 for the x value. And then I have a minus 2 out there for k, so my vertex is going to be at negative 3, negative 2, so right there. The axis of symmetry is at the x value of the vertex. So it's at x equals negative 3. But to finish graphing, I need 3 points. So I have 1 point, I have the vertex, but I need to pick an x value to the right of the vertex and an x value to the left of the vertex. And truthfully, we'll see in a second, I'll explain why we really only need to find 1. But to do that, so over here, so to graph other points, we need to choose an x value. So any x value to the left or to the right of the vertex, and I need to plug it into my equation. So I'm going to plug in 0 only because I like plugging in 0. Actually, that's going to be a poor choice on this graph. We'll plug in negative 1. So I get to choose the x value that I plug in. It doesn't matter what x value you choose as long as it'll show up on the graph. So if I finish this up, I have 2 times 2 squared minus 2. So I have 2 times 4 minus 2, which is equal to 6. So I chose negative 1. And the point that I'm going to put on my graph is negative 1 because that's the x value I chose. I chose the x value negative 1, and it gave me a y value of 6. So I'm going to put a point at negative 1, 6. And what I meant by you really only need to find 1 is we're trying to build our u here. Our quadratic is a u, so we're trying to build a u. The axis of symmetry is here at x equals 3. You don't actually have to graph this. So if this point is 2 away from the axis of symmetry, by definition of what symmetry means, there also has to be a point over there. Which means if I find 1 point, I know that there's another point on a mirror image on the other side of the axis of symmetry. And then I've built my u. So I still need to identify the vertex, just like absolute value. Then I need to pick an x value and plug it in to find the y value that goes with it. Then once I get that point, I just need to travel along the axis of symmetry, basically fold the graph over, and I'll find my other point. All right. The last question it asked me is to state my transformations. So A, H, and K do the same thing that they've always done. So I have an A value of 2. So that means 2 is bigger than 1. So I have a vertical stretch by 2. H moves me left and right, and it's a liar. So since I have plus 3, that's going to move me left 3. And then lastly, I have a k value of minus 2, which means I go down 2. So the transformation rules are the same that they've always been. They're not changing for quadratics. All right, we've got our last example here. So here I have a graph that's in intercept form. So first, it asks me to identify the intercepts. These intercepts are similar to h. They're in parentheses with x. So that means that they are, in fact, a liar. So the first question just asked me, state the x-intercepts. So the x-intercepts, if h is a liar, they are at 1, 0, and -3, 0. And again, how I got that is in one parentheses I have x minus 1. So that means the x value is actually positive 1. And then on the second parentheses I have x plus 3, which means the x value is actually -3. So now that I know those, I'm just going to graph those x-intercepts. Now I need to know the axis of symmetry. The axis of symmetry, if you look at the notes that we took a couple slides ago, happens at x equals r1 plus r2 over 2. Basically, that just means that it happens directly in the middle of those 2 points. So, -3 plus 1 over 2 is -2 plus divided by 2, which is -1. So my R1 and R2 are -3 and 1. It doesn't matter which one's which. Are -3 and 1. So I plug in -3 to 1 into that equation we wrote down. And it tells me that my axis of symmetry is at x equals -1. That means, and if you think logically, again, we don't have to draw the dotted line, but I'm going to for explanation purposes. So if you think axis of symmetry, these points should be directly mirror over the axis of symmetry. So if you look right here, that point is 2 away from the axis of symmetry, and that point is also 2 away from axis of symmetry. So if you have a graph and don't remember our fancy little formula, you can just look at the graph and know that both points should be equidistant or the same distance away from that axis of symmetry. So the third question that I've kind of covered up a little bit is, what's the vertex? So if I was asked to find the vertex here, in vertex form it's just hk, but I don't have that luxury here because I'm not in vertex form. So to find the vertex, the x value of the vertex is the axis of symmetry. The axis of symmetry is the x value of the vertex. Therefore, the x value of the vertex is the axis of symmetry. So I know already that the x value is -1. So if I know the x value is -1, and I have an equation to find the y value that goes with it, I just need to plug in -1 everywhere I see an x, and then when I solve this out, I'm going to get the y value of the vertex. So to find the vertex, the x value of the vertex is the axis of symmetry. The y value we have to plug in and solve. So we have -2 times 2, which is -4. So my vertex is at -1, -4. Right here. And I make my u. All right, so in intercept form, we can find our x-intercepts. It's just r1 and r2. The axis of symmetry is directly in between those 2 points. So we're just going to take the average of the 2 x values, or r1 plus r2 divided by 2. The vertex, the x value of the vertex is the axis of symmetry. So after we find the axis of symmetry, we just take that x value with us. And the y value, we actually have to plug in the x value and find the corresponding y. All right, so that's our video over forms of a quadratic function.